So welcome to our Tuesday talk series. This is a series that happens every week that we have school in process and progress. And we beam it out on CMU-TOCS, C-O-T-O-C-S, so anyone can watch it. We also put it online, and as a legacy, it's a really nice thing for a lot of the speakers to be able to point to their talk that they gave here. The talk will go from 1:30 to 2:45 or so. I mean 25, excuse me. And we like to be out of here at 2:30. We really prefer that people have all their questions out in the hall with the sodas and the cookies. And that's a nice time to learn more about the speakers and for them to learn about us. Logistically, I'm going to turn on all the microphones so that you can rattle your keys on the table to make lots of noise, actually so that you don't have to push the button to ask questions. So everybody can ask questions whenever they want. And I want to just say that what we've been trying as an experiment this semester is there's a speaker series that is funded by Jim Sporer, University Liaison for IBM Worldwide, about service science. And bringing that into the talks series has been something we've been trying this semester. We'll get some feedback and see if that's a really great idea or whether that was just an experiment. In any case, I want to bring Jim up to introduce the speaker of today. Very excited to have you.
Thanks.
And thanks for
coming. Thanks, Ted. So, welcome everybody. I'm Jim Sporer with IBM University Programs Worldwide. It's my pleasure to introduce our speaker today, Jon Pittman from Autodesk, and his colleague Bill O'Connor from Autodesk is here. Jon is the Vice President of Strategy at Autodesk, and I just want to say we've got two of the best forward-thinking minds at Autodesk here today to share with us some thoughts, and I think you're going to be amazed. I know I was amazed a month or two ago when I saw Jon's presentation. I had no idea what Autodesk was up to about the design of buildings and even whole cities, and you're going to see some really amazing stuff today. And Jon is a great person to take us through it. He's an architect. He has degrees in architecture and design, as well as computers and graphics. So without further ado, Jon.
Okay, thanks, Jim. So I'm going to try to give you a picture of what design is about and how it relates to really moving beyond the design of things, which is mostly what our customers do, to the design of nodes and networks. So I'm going to try to give you some of the lessons we've learned about design over the years. So humans have been designing things kind of ever since we became tool makers. So the person who designed this arrowhead actually did go through a design process. It was probably a very unself-conscious design process, but he had some intention, and that's really what design is about. Is we have an intention, we want to do something, and obviously the methods and tools that person used were fairly primitive. Today we can produce some pretty amazing things, some very complex things, and it requires more sophisticated methods, more sophisticated tools. But one of the things that I think we're seeing is that the demands for designing things, designing a complex world, in some ways are overrunning our methods and tools. So we need to think about how we take those methods and tools forward to design even more complexity. A new iPhone. Thinking about complexity, a lot of things. If you look at the car, that also turns out to be a very complex system. So it really is a collection of systems. If you think about it, we have the skin of the car, the body. There's a powertrain, there's a drivetrain, there's an electrical system. There are the equivalent of avionics for an airplane in the car. There's a structural system. We have to have all these things integrated and working together. So something which is fairly utilitarian and started as a fairly simple thing now is a very, very complex system that we have to design. And so our design techniques have to really be able to master the collection of all the different systems and how they integrate. Even entertainment used to be fairly straightforward. So it used to be the director would point a camera at an actor and say, action, go. Now technology is really coming in entertainment. So in Avatar, Cameron used some of our software to do this, and he's able to create creatures that don't exist in the real world, and yet they're believable creatures because we can embody them with human-like emotions, human-like gestures. There's an enormous amount of technology that goes into this. So something that was very simple in terms of the techniques of storytelling now becomes very complex. Even this simple wind turbine is an integration of several systems. There's a structural system to hold it up. There are power systems, power generation systems, and so forth. So more and more we're seeing an amazing amount of complexity. If we look at these two examples of keys, these are both keys. If you look at the one on the left, on the right, sorry, get my directions mixed up. You look at this one. The one on the right, that's a simple mechanical thing. All we really had to care about was its shape. Look at the one on the left. That's also a key. It does the same thing. It provides access to something, but it's an integrated system in about the same size package. So it not only has mechanical properties, it has electrical properties, it has radios, it has software, an enormously complex thing. A lot more function, too, but it still does the same basic thing. So we're seeing as society goes forward, more and more complexity in the things we have to design. So this is just an example of the kind of complexity. This is a set of building mechanical systems. And you see, it looks like it's a spaghetti, and in fact it kind of is, but every one of those pipes or ducts has a function. And a big part of the challenge of designing for this is making sure those things actually all interrelate and don't conflict with each other. Turns out in designing complex systems like this, conflict is a huge problem because different people are working on getting a picture of the whole thing is a really big challenge. So we're seeing this increasing complexity in the design of things. And some of that complexity comes from good causes, things like new methods and materials. And as we go forward, we're seeing some pretty amazing new materials. At Autodesk, we're working a lot with 3D printing, both at the micro level and the macro level, looking at the actual printing of things like buildings. So new methods and materials give us complexity, but they give us great possibilities. We see increasing performance expectations, a lot of technological development. There are also other things that are not so good that are giving us complexity, things like economic volatility and competition in the global market. So both positive and negative forces are increasing complexity. But we know that complexity is there. So when we think about designing of things, so this is a city, one way to think about this is a collection of nodes and relationships. So if you think about this, each building in this network is a node. And it was designed by some organization, it's owned by some organization, managed by some organization, typically independent of all the other nodes. And yet the city itself acts as a network. We often have conflicting priorities. So for example, this road, the traffic authorities are going to want that road to be as efficient as possible for traffic. And the fire department's going to worry a lot about disaster access and those kinds of things. Those are conflicting priorities with the Parks Department, which wants to actually help people move across here so they can enjoy the waterfront. So one of the things we have to deal with in these complex systems is figuring out how to balance all the different priorities. And even before you can balance them, actually see the different priorities. Then if you think about the individual building, the building itself is a system. So it's actually a collection of systems. So we've got a structural system, a skin, mechanical system, fire protection system, electrical system, water distribution, water treatment, or water getting rid of wastewater. So each of these is a system that we have to put together. Again, each of them in and of themselves are a very complex system. So here you get sort of a recursive problem. You get the city itself, which is a system, and the elements in the city each are a system themselves. And of course, when we look at networks, we all are now part of networks. So if you look at something like Facebook, we're all nodes in a network, but we get the benefits, and some say the challenges, of being part of a larger network. So when we design things, and I'll use buildings as examples, we do have to think about this integration of systems. This is California Academy of Sciences in Golden Gate Park, and we have to think about, people know the roof here, but to make that roof work, there's a structural system underpinning it. There are mechanical systems that support it. So when we design these things, we have to really think about this integration of systems and various elements. And again, coming back to where I think we have to go, we have to kind of move our thinking and our techniques away from the individual elements. These are still important, but we also have to think about how all these elements relate in this system. That's what will create humane environments. That's what will create effective environments. So I wanted to give you a little more context in the design of things and talk a little bit about who Autodesk is and more what our customers do to give you a perspective on what design is about. This is the vision for the company, helping people imagine, design, and create a better world. And when we talk about design, that's kind of a loaded word. There are a lot of different interpretations of the word design. If you go up the road here to IDEO, they'll have one definition, probably closer to my definition. If you look at the New York Times culture section, they'll think it's more about fashion and style. So I think a great definition of design, the one I was educated as an architect, so the one I would use, is this melding of form, function, and performance. So if you look at this car, we care about the form, we also care about the performance and the function of the car. And you have to have all those three things in balance, in my view, to have a good design. So we're all about helping people design. We do that by making software tools. So we're a software company. We don't do any design ourselves except for the design of the software. And we help people, we say we help them experience their ideas before they're real. And that's a pretty key concept for designers, because what they do is imagine the future. And it's not that easy to imagine the future because you have to actually make it concrete. So a lot of the tools we're doing help them both make ideas concrete, but also understand the consequences of their design decisions. That's particularly important when we talk about this idea of a network. Because it's easy to understand the consequences of my design decisions if I'm designing an object and I want to change the shape. That doesn't affect a whole lot. If I'm thinking about one of those buildings in Pudong, the Pudong district, the shape may actually aerodynamically affect a bunch of the buildings around it. So the more interlocked we get as systems, the more we have to understand context, and the more we have to understand relationships. And in particular, the more we have to be able to see and understand unintended consequences. So the markets that we're in are three big markets. The first is architecture, engineering, construction. Our former CEO, Carol Bartz, more recently of Yahoo notoriety, used to say, if God didn't create it, one of our customers probably did. And that's a little bit of an overstatement, but not much, because we really deal with a lot of the man-made world. So architecture, engineering, construction means buildings, roads, water systems, transportation systems of various kinds. So most of the built environment. Chances are anything reasonably new here was touched by an Autodesk product here on the campus. Also manufacturing, so anywhere from industrial machinery to this exhaust manifold. Automobiles, all the major car manufacturers design their cars with our software. Smaller products like toasters and consumer electronics, all kinds of things. And finally, entertainment. Most of the special effects are done with our software, and the characters and the content in most games. And what that does is it gives us a pretty unique perspective across all these design disciplines. Turns out that while if you talk to someone who's an industrial designer making manufactured products, they'll claim their approaches are very different from a movie maker. When you actually get them in a room and talk, first of all, they're fascinated by how each other work, and they learn from each other, and it turns out when you factor out what they're doing, they're all fairly similar processes. So it's all about some of the same kinds of things. It's about these things. Really designing a solution, come up with an idea, being able to visualize that idea, and then being able to simulate performance. So the kinds of things we do are all about that. So we help people sketch and model ideas. This is a conceptual view of a car. I'm trying to understand the configuration and the performance, and really the feel. What's it going to be like emotionally to sit in this vehicle? We also help people visualize. So this is not a photograph. It's a computer-generated image. But it gives a pretty strong sense of what this particular space would be like. And finally, simulating performance. So here, it's like we're simulating structural performance, but we're also looking at the assembly process of how this thing goes together. So the whole history of computer-aided design started in about the 1960s. Actually, we were talking, Ted and I were talking about the Media Lab. Nicholas Negroponte, who was he was the founder of the Media Lab, wasn't he? Sort of.
Oh, yeah, no, not just sort of.
Yeah. So Negroponte actually kind of was one of the early people who defined this. this idea, but the whole history of using computers to design things has really tried to deal with the problem I'll show here on this diagram. So it's a little bit complex, but this is effort to effect. This is time. And I'll use an architectural example, but to give you kind of a sense for those who are not familiar with the architectural process, this is really kind of the conceptual phase of design over here. So this is kind of where we just have a concept or an idea. This is where we're developing it and fleshing it out. This is where we're creating it. So construction, this is construction administration in the architectural world. And this is where we're operating it. And of course, we're showing that if you really look at most things, this part's very small, and operations runs out there for a long, long time. But if you look at the process and look at where effort is, this line shows, coming down, the ability to affect outcomes. So when we just have a concept, we can really swing the outcome very, very dramatically because the concept really shapes the ongoing result. As we get farther and farther through the design process, our ability to affect the outcome diminishes pretty dramatically. And that's because we've made decisions, we have constraints now, we have to kind of live with the result of our previous decisions. If we look at the cost to make a change, it's exactly the opposite curve. We can make, when it's just a concept, we can make lots of changes. We get down here in construction, it gets very costly to make a change. We get out here in operation, if it's a building, we're talking jackhammers, a lot of cost and a lot of noise. It's very expensive to make changes. If we look at the typical design process, where do we spend our effort? Again, this is the architectural design process. This is called contract documents. This is making the drawings. So the problem with this diagram is you can see where we're spending most of our money, most of our effort, is here where we've already got the concept down. Our ability to affect the outcome has diminished quite a bit. The cost of change is rising rapidly. So what we've been trying to do in the field of computer-aided design for the, 60s to the 90s, or 60s to 2010, so what's that, 50 years that we've been working on this problem, what we've been trying to do is this. Shift the curve this way. Shift the curve to the right so we can understand our design more. What we want to do is understand the consequences of those design decisions earlier and earlier in the process, at a time when we can affect the outcome more dramatically and the costs are lower. So all the things we've been doing and all the other people in computer-aided design have been doing have been all about how do we move our thinking further upstream? How can we tell earlier what the consequences of our design decisions might be? So that's the essence of the problem. So now I've described how we talk about designing cars and buildings and movies and those kinds of things. I think as we move forward, we have some pretty interesting design challenges. And again, being kind of coming from a design background, I sort of view the world as a series of design challenges. So I may be interpreting more broadly than you might interpret design, but I actually think the approach designers take is important here. So one is globalization. Globalization has created great challenges, also creates great opportunities. The opportunities certainly are the ability to, if you look at the economic view, that free trade creates more opportunity. It's there. As we move literally massive numbers of people into the middle class, it creates huge new markets and huge new opportunities. As places like China and India have more middle class societies, those are great markets, great opportunities for growth and development. And certainly for those people, great opportunities for them to increase their standard of living and their lifestyle. The challenge is, whether you're a country, a company, or an individual, is that competition used to be local. It used to be, if you're here in Silicon Valley, your competitors were here in Silicon Valley. Now, of course, they're all over the world. So it's increased the level of competition worldwide. Now, as a society, that's actually a good thing because that pushes everybody forward. As individuals, it means we have to always, we're always competing. So that can be wearing at times. So globalization provides great opportunities and great challenges. Now, the next one, the next challenge that we see, and this is particularly germane to us because about half our business is servicing people who do the built environment, is urbanization. Last year, the year before, we passed the 50% mark. 50% of the world's population live in cities. And that rate of urbanization is really dramatic in the emerging economies. People are moving from agricultural lifestyles to urban lifestyles. And if you think about it, both China and India will have to build over the next 10 to 20 years the equivalent of the U.S.'s urban infrastructure. So think about that. Think of all the buildings you've seen in the U.S., all the buildings, roads, bridges, dams, airports, ports, everything. Building that equivalent it's been built over 300 years, building that over a period of about 10 years, 10 to 20 years. We did that with an abundance of land, an abundance of labor, an abundance of talent, an abundance of raw materials, abundance of energy.
Controls.
Abundance of controls, yeah. All kinds of things which don't exist in some of those places. So the rate of urbanization is very rapid. Now, one of the challenges, if you look at the construction industry, it's one of the most wasteful industries on the planet in a couple of ways. In the sense of just environmental waste, about a third of landfill waste is construction waste. When you tear down a building and all that junk has to go somewhere, about a third of our landfills are construction waste. Also, about a third of the dollars that go into construction are wasted dollars. And most of that's from information inefficiencies. Anybody who's kind of watched a construction site knows that. There's the crew that shows up one day, but the materials haven't arrived, or two crews are trying to do the same thing at the same time. So a huge amount of informational inefficiency, and the way we construct is just terribly wasteful. And one of the challenges, if you go someplace like China, which I've done, and talk to them, they want to build just like we do. And telling them, no, don't do that. We've kind of screwed things up. We want you to do it differently. It's kind of a big sell because they say, hey, you're the most advanced economy in the world. We want to be successful like you are, and trying to convince them that they actually could do better by adopting different methods is a challenge. A couple other things with urbanization. When we think about things like climate change, about 60% of greenhouse gases actually come from mostly heating buildings and conditioning buildings. So while we focus, a lot of the world focuses on vehicles, cars and things like that, it's about 12%. So the impact of buildings on the environment is huge, yet we're not doing enough to deal with that. So as we look forward, these are big systems problems of how we deal with urban environments and how we make them both humane, sustainable, and also more effective in the way we actually create them and build them. Now, the picture I showed of Pudong, that's the picture people see of China from across the Huangpu River. See these beautiful buildings. If you go about 45 minutes away from there, you see these apartment blocks that are kind of like the best of Soviet-style housing projects. Those aren't very humane environments. So just even creating environments where people can live and have a high quality of life is an urban design challenge. Certainly healthcare is another one of these network problems. The real challenge is how do you provide healthcare at scale in ways that reach lots and lots of people without the massive costs that we incur in our society and kind of the crazy policy and politics that go with this. So that's, again, another network problem we have to think about holistically. And finally, climate change. The reason I like this particular picture is think about the person who designed this plant. They were actually thinking about the node and not the network. Clearly thinking about this problem of spew. They weren't planning to spew toxins into the air. The problem they were assigned was to generate power. And this was an externality. This was something they just didn't care about. We can't design like that going forward. We actually have to think about all these consequences of our actions because we can't afford this kind of thing. And whether we're restricted through policy, through public opinion, or what have you, we have to think about this. So this is an example. I think a lot of the climate change issues are a result of designing in the small rather than designing in the large. So one thing all these problems have in common is that they're systems problems. They're connections of nodes and networks, or nodes and connections, they're networks, and all the things in the network, they affect each other in sometimes ways that are obvious, but often ways that aren't obvious. So a lot of what we need to do as designers is think about how to see the consequences of our actions, how to understand these networks, how to relate to them. So I think some big challenges there. I want to talk about the tools we have, and not so much the tools we have today to design, The tools we have today are pretty amazing. They can create pretty good representations of things. What we've really been focusing on over the past 50 years is creating good representations, and we'll continue to do that. But I think there are three technological trends that are coming along, or are here for that matter, that really are going to affect the way we design and think about design, and they'll relate to the design of these networks. The first is infinite computing, and we specifically call it that. It's kind of related to the cloud. But when people think about the cloud, what they often think about is putting all your data where you can get to it. That's important for us as designers, and connecting people together. What's really interesting from our perspective is this idea of infinite computing, having infinite computing resources effectively available at zero cost. So why is that important for a designer? Well, if you think about how we've designed things in the past, we've operated on a conjecture analysis model. We'll make a conjecture. Here's an idea I have. Let me represent it, and then let me use the computer to analyze it. And typically, we can only do a couple of iterations because computing power has been expensive and the modeling has been expensive. So if you look at an architect, for example, architects typically are assumed to hit their prime at about the age of 50. And the reason for that is they've built up enough experience to know when they make their first conjecture, it's going to be in the zone of right. But then they make a conjecture, they can tune it a little bit more. That tends to be a fairly conservative kind of design process. And they can't explore the whole solution space because they're basically creating solutions based upon their past experience. Well, with effectively infinite computing resources, we can change that. We can use that conjecture analysis kind of process as we go forward, but we can do the loops much faster. We can create conjectures, get the results back, another one, another one, another one. So as much time as we have, we're gated by our time, not by the computer's time. What's even more interesting, though, is we can actually change the relationship. This actually does go back to Media Lab, Negroponte early days, where rather than do this conjecture and analysis, we can actually have the computer generate things. So this is an example of a building in Korea. And the fundamental design idea that the designer had was he wanted a square base and a round top. And that seems fairly simple, but if you look at all these elements, you know, each floor has a slightly different configuration. And that would be tremendously hard to do by hand, but you can just generate it with a computer. He also wanted it to be a sustainable building, so he actually calculated the normals of each piece of glass. So each of these little dots is a pane of glass. He calculated the normal of a piece of glass relative to the normal of the sun at a typical time of day, and then he could slightly change the orientation of the glass to minimize solar gain. So again, that's something that he could maybe envision the concept. He couldn't actually realize it until he had a pretty high degree of compute resources. Another example is, I think this is a vehicle to take supplies up to the space station. Again, an aeronautical engineer would typically make a conjecture based on their experience and a body of knowledge about airframes. Say, here's one that might work. We'll start tweaking and tuning it to these conditions. If you have the ability to simulate in the machine different configurations, not only can he make conjectures and come up with different ideas, you can actually ask the computer to go generate a whole range of solutions and may come up with things that he wouldn't have imagined because the computer's not constrained by the solution space of his mind. So we actually believe the cloud, the infinite computing embodied in the cloud will really help us, gives us a lot more capability to help see the consequences of our design decisions. You know, the challenge becomes representation. The next thing that we think is going to be pretty important is the ability to capture reality. So you're probably familiar with these sensors, very small, very cheap. They're parasitic, so they draw power from the environment. They're cheap enough that when you're designing a building, or in fact, they're doing this in the Bay Bridge, they just embed them in the concrete. So when the earthquake in '89 happened on the Bay Bridge, they had to go out and look at everything to see what moved. In the new Bay Bridge, they will know instantly. In fact, they know, we're getting all kinds of seismic activity all the time. They know exactly what's happened, because the New Bay Bridge is all metered with this. So this lets us do a number of things. This is 210 King Street in Toronto, one of our facilities. We've metered that building at a very high level of granularity. So we know, for example, what the occupancy load is. When you're thinking about energy use, you make a bunch of assumptions about who's in the room when, who's where when. Usually those assumptions are wrong. And we assume people work 9 to 5 and things like that. So we've measured who's where, because they're actually consuming resources and generating heat. We've measured the temperature, the airflow, air quality, all kinds of things about this building. And what that lets us do is both improve our design models, because we can feed back what really is happening, but also move the building from a static thing that we kind of designed at one point and then operate to a more dynamic thing where we can actually adjust it based on conditions as we go forward. Scanning technology is getting to the point where we can now capture reality as well. So here's an example of a point cloud of a building. This is a scanned point cloud, and here we're doing feature recognition. We're actually trying to understand what that point cloud represents. And we're doing it semi-manually now. Obviously, at some point in the not too distant future, we can do this automatically. Now it's guided. But you'll see we're taking all this point cloud data, all this stuff, and actually turning it into a model of a building. Like this. So when you take reality capture plus the ability to measure and monitor building, you get this ability to take whole new environments and really get a picture of how they're performing and how they're behaving. Again, you can do this with products, with all kinds of things. In fact, if you go back to Avatar, the approach they used to make Avatar was very much like this. The reason you have such lifelike expressions in the Avatar characters is that they placed little dots all over human actors' faces. They had them act as if they hadn't act. So acting is about projecting emotion into a situation. They could then take those points and map them into this other character. That's why the characters are so lifelike, is they weren't synthesized, they were actually projected from capturing a real live actor who knows how to project an emotion. So the last thing that we see really affecting the design of things and systems is mobile devices. So this smartphone has more computing power than the space shuttle, the first space shuttle carried with it when it was launched. And if you look at the statistics, they're pretty staggering. Mobile devices of various kinds, like these things, are growing exponentially. There are about 10 billion on the planet right now. If you kind of know the pyramid of population, that means there are a lot of them for those of us who are pretty wealthy. I've got 2 with me now. These are people who walk around with 10 of these things. And they're still growing very exponentially. So the number of mobile devices is something that we think is going to fundamentally affect work. Now that's important in, again, understanding the consequences of our design decisions, because our design decisions, the consequences are often distributed out in the environment. So this is a building situation. What's happened in the past, and part of the reason for that 30% economic inefficiency I talked about is decision latency. So if this guy here was having a problem, he'd call back to the designer's office and they'd try to figure out how to resolve the problem, and there's maybe a couple of days latency. Well, now the designer can be right here, understand what the intent was, create much less, reduce that decision latency. So moving computing to where the work is one aspect of this. Also, there are a lot of people who can benefit from understanding the information. In this case, if you look at assembly problems in factories, I know about 10 years ago I was at Train in Wisconsin, and the factory manager there said, at the time unemployment was really low. He probably still has the problem, but he said the problem was he was hiring people who dropped out of 7th grade. That was kind of his best he could get at the time. And he said they just have a hard time understanding. They can't read drawings. They can't understand how to assemble things. But I can show them how to assemble this. They can see pictures. They can see animations. They can understand how to put these things together. So really helping, creating the ability for a broader swath of society, something we were talking about at lunch, to do more is another thing that these kind of devices will do. We've actually been experimenting with, on your iPhone, you can get an application that lets you draw with your finger. You might kind of think that's a dumb idea, but there are literally millions of people now doing this. It's kind of funny, in our we have a little consumer division that does this and other applications. The company's been in existence for about 30 years, and the legally licensed software that we've deployed that we know about is about 10 million units. Our consumer division's been in existence about 18 months. They've done 10 million units as well. Now, those are units that are free or 99 cents as opposed to $3,000 or $4,000, but still, it's a whole different world. And what we find is people are really engaged. This is kind of unleashes their creativity to have this kind of application. And of course, when we think about mobile devices, these kind of form factors are what we have today, and they'll probably exist for a while, but they're kind of transitory. As you look forward, this may be a little hard to see, but there's a projection system here where she's looking at projected imagery. So as we really think about how we interact with the world, having approaches that really let us see the world in an augmented reality kind of way are probably more going to be the norm. So lots and lots of possibilities. These are not the end game. They're the intermediate game. So what does this mean? How does this relate to designing these big system problems that I was talking about? Well, I think if you look at root, what we try to do with design tools, they're amplifiers for the mind, and this does go back to early Negroponte kind of thinking. That's what they do, and that's what we've been trying to do over this 40, 50-year period, is to really amplify three things: cognition, our ability to think; collaboration, our ability to work together; communication, the ability to tell the world. So when designers work, often a misconception, people see a designer drawing or making a model. And the misconception people have, including a lot of our developers, our programmers, is they're documenting the result of mental activity. They've thought of the idea, and now they're just drawing it up. That's not true. When people are designing, there's actually a connection between the mind and the hand. And as you create, you're evaluating your understanding. So what we're trying to do with digital tools is help people think. Create ways for them to make these conjectures, see the results, and really build jointly with the computer a mental model of what's happening. So that's the first one, is cognition, tools to help cognition. The second one is tools to help collaboration. As we deal with more and more complex problems, and we get a more complex workplace. In the workplace, we have certainly multiple cultures. We have multiple generations. The thinking on generations now is they're not 20 years, they're about 6 years. So they're not biological anymore, they have to do with worldview. People born 6 years apart have a totally different way of working from each other. And then you talk about disciplines. Someone who comes from a software background, trying to communicate with someone who's designing an electrical system. How do those groups relate? So one of the things that we can do to help them relate is to create shared representations. So if we create a shared representation, there's one representation, the single source of truth, but we can look at that through the various lenses of the people. We can create more common understanding of what it is that we're producing. And that's a huge problem in any kind of complex problem, is the different worldviews people have and different set of concerns. So if we can create one common representation, that helps a lot. And the last one, which we shouldn't underestimate, is the ability to communicate to the general public. So one of our customers is Bart Ney. Anybody recognize that name? He's the Public Information Officer for Caltrans. So you've probably seen him on TV or heard him speak. So his job ranges from going and testifying at the legislature to explain to the California legislature, which is not, as you know, in a mood to spend money, why they need to spend billions of dollars on this bridge. He has to explain to the general public. If you look at so this is the new Bay Bridge. Its design is actually very innovative. It's representative of the Golden Gate Bridge. And they had a decision, do they want a utilitarian bridge like we have now in the Bay Bridge, or we want to really make a statement that kind of brackets the Bay? And so they had to convince them to do that. He's the guy who talks to the general public and says, by the way, on Labor Day, you don't want to drive across the Bay Bridge because we're taking a big chunk of it out. And he also works on communicating to construction workers what sequence is actually happening. If you remember when they closed one of the Labor Days, everybody was worried they were going to be closed for 4 days. They're estimated 3. Everybody thought they were going to be closed for 4 because everybody knows construction never happens on time. what they did is they actually created animations and played them for the construction workers. So everybody knew at any given moment where each piece of equipment was, where each person was supposed to be, what they were doing. They opened in 2 days instead of 3. So that's all communication. And Bart has talked to us a lot about the value of doing this. He said, I can talk until I'm blue in the face about why we need a bridge like this. But if I can show the legislature, if I can show the public, then that makes my job not just easier, but possible. So just to tie it back to this, one of the things he commissioned is an application that runs. You can download it from the App Store. It's called the Bay Bridge Explorer. Which lets you drive across the Bay Bridge. And you can get it, if you don't have an iPad, you can get it on your phone. Same application. So it's actually a driving simulator. They created one that we have in our offices in San Francisco where you can sit down and drive, but you can sit with your iPad or your phone and drive across the Bay Bridge. So this is an example of taking these techniques and being able to communicate them broadly. So we've learned, literally, tens of thousands of years, we've learned about the design of things. And the design of things is getting harder and harder because they're becoming more complex. What I hope you'll take away from this is there are a lot of lessons in the design of things that we can apply to the design of systems and some of these big systems problems. And doing that requires that we think about the nodes, buildings here, and the interconnections between them. And think of everything we design in at least one outer context, if not multiple outer contexts. We also think recursively internally. So each of these nodes is, in fact, a set of complex systems. So when we think of design, we need to think about both the nodes and the networks. We need to think up and down in context. And as we create tools to help people visualize, simulate, and analyze their decisions, help them create better design decisions. So a lot of this is all around creating the ways for people to understand the consequences of their design decisions. Thanks. Yes.
So I've kind of been around these guys from NIST that talk about making executable standards. So these standards then would be not just something that you check if your design is good to, but actually they actually play a part in design. And there's two parts to my concern about this. One is it's very exciting. It seems maybe I'm interested in what you think about this from that point of view. And then the other question is if you have to make everything agree, what you have to do to make these things work together. So.
Well, that's a huge. There's a bunch of answers, a bunch of topics in there. I think on the issue of to what degree do you have standards? And standards are almost always backward-looking, right? So
these guys are making them executable. They're making languages that will be programming languages.
Yeah. So in the building code, for example, there are two kinds of standards. One's a prescriptive standard that says, thou shalt have exits from this room no more than 30 feet apart. Then there's another way to do it is a performance standard that says everybody in the room needs to be able to get out in 10 seconds. And the performance standards, they're harder to evaluate, but they give you a lot more design freedom because 2 doors 30 feet apart is kind of, you don't have a lot of freedom there. There may be much better ways to evacuate the building if you're conforming to a performance standard. So if they're doing these in the sense of a performance standard, that's much better because it doesn't create backward-looking, kind of locking you into old paradigms. There's been in these various markets that we serve, there's been a lot of debate around standards of interoperability and communication of data. And we've had more success in the mechanical products, less success in the built environment. And part of that has to do with the built environment is composed of lots of, mechanical world, manufacturing world, first of all, you have integrated organizations, so they're more used to having more integration of process and practice. The building world's tremendously distributed. It's tremendously distributed. If you look on a particular construction site, there's a construction manager, a general contractor, the painting contract, there's a huge number of subcontractors. So buildings and movies, for that matter, are quite similar. The people come together, the teams come together, build them, and then disperse. And what that does is that it's a network, it's an economic network. And what happens when you have economic networks is they're terribly conservative. They're resistant to change, which is one reason the construction industry's still got 30% waste after we've identified this many, many years ago. So I think one of the challenges is how do you break those work processes? When you have a more vertically integrated industry like manufacturing, you can create those standards. So there have been a bunch of attempts to create data exchange standards. Part of the issue is that we haven't really understood what the data is and what it's about. A couple of my friends who practiced architecture quite a bit, will say in architecture, and the way buildings are built, there's a lot of tacit knowledge. So the architect doesn't define how you're going to attach this surface to this wall. They just say, put this kind of surface in. And the knowledge comes from the manufacturer and the person who installs this. So there's a whole bunch of distributed knowledge. And so the idea of having a representation that has all the knowledge that we need to build the thing is a little bit flawed relative to the structure of the industry. So we need to kind of reconcile that. How do we take that tacit knowledge and make it explicit, or do we even want to do that? We have to kind of decide that. So did that kind of sort of address your questions?
As you say, there are lots of ways to go with this issue.
Okay, yeah.
What's your opinion of how the tablet market will shake out between iOS, Android, and Windows 8?
My opinion, well, you can kind of see what brand I use. So I'm a pretty big Apple fan, although I have a Sony Vaio too. So I think I guess one way to answer that question, the biography of Steve Jobs came out Monday. There's been a lot of press, pre-release press over the weekend. And I was telling Bill I saw a quote. Bill Gates had said something about Steve Jobs didn't really understand technology, but he had this kind of remarkable understanding of what works. And the person who was writing the quote said, maybe that explains the difference in the two brands which those two people were responsible for. So, which I think there's some truth to that. So I personally think Apple's going to drive this. I think we'll always have a market for multiple devices. I think Apple's been way ahead, in my own view, in these kinds of things.
Do you think they'll stay ahead even with Windows 8?
Yeah, I think so. Well, let me put a little caveat in there. It depends on what will happen with Apple's culture. You get to the question of, is Apple's culture, will it survive intact Steve Jobs passing? So I think if that design kind of culture, I like to think they have one. I think a design culture ultimately over time will trump a technology culture. But we'll see. It's a good question. Jim.
So, given your extrapolation of Moore's law, and you think that's going to develop, and how you've seen the complexity of these models evolving, where do you think we'll be in like 10 years and 20 years with the complexity of these models?
Well, I think that first of all, the complexity has always been there. It's getting worse, but it's always been there. We just haven't been able to understand it. So we've solved a lot of problems by partitioning the problem.
Right.
Saying I'm going to ignore, and which is, if you go back to the picture of the power plant, we solved that problem by partitioning it and saying, my job is to generate power. I'm going to, get rid of the waste this way and this way. I think as we get to a more interconnected world, we have, as we get more crowded on the planet, we have to deal with those externalities and those connections. So, and part of it is the complexity is always there, but now we're forced to deal with it more. But it also is increasing. If you look at the key example, right, that old key was simpler, and you can actually solve, 90% of what the key was trying to do with that old key, not the new key. Not that we have cars that are driven by little forged keys. So I think the challenge is we're both going to be forced to deal with complexity. Complexity is going to increase. I think the challenge for those of us making tools is how do we help people see that complexity?
Just one of the things we talk about with our CTO is exactly this idea. We refer to the world's complexity as a giant C.
Yeah.
And traditionally, what we've had to do with our tools is to oversimplify a chunk of that world and bring it into the computer, and it's like a crappy version, we write it as a small c,
Right.
and then somehow we're stunned that when we try to extrapolate it back out, it doesn't fit. So the key principle, I think, will be the idea of massive complexity growing. Like all the stuff on the slide, is most of it's been there. But if you talk about like Berkeley tracking the amount of information in the world, all the metrics are just exponentially, right? However you term complexity, I think the idea will be massive complexity out there. But you said one brain problem. I'm one brain. The tools and the technology and the systems have to dumb it down right to the right amount so I can do one brain activity on it, and it's got to go right back up into the complexity. And that's where the cloud comes in, I think.
And there's another aspect to this too, and it's something we deal with all the time, is people naturally assume that we want to create higher and higher fidelity models. In fact, we do, but if you go back to this picture I had a while ago of the car, wherever it is, you know, it used to be, oh, here we go. And when I was studying computer graphics, we had a guy who had come through and convinced Don Greenberg, the guy I studied under, that we needed to create higher and higher fidelity representations of things. When in reality, if you look at this car, it's a low fidelity representation. It's someone sketched it. And people who design these kind of things learn how to sketch this way. And there's a real reason for that. One is they want intentional ambiguity. So they don't want, they want you to get the feel, but they don't want to have everything perfect. There's a couple reasons for that. One, they can represent something imperfectly and not have to do all the work to model it. But also, they want your reaction. So think about a presentation. If you put together a bunch of slides and you show them to someone and you've really labored over the fonts and everything's perfect, they're going to be reluctant to say, change that. It's wrong. Unless you're our CEO, which Bill and I work with. He's not reluctant.
He violates that law.
Yeah. But most people are going to say, no, don't change it. So in fact, doing something like this, I can say to you, how do you like this? And you're going to be more inclined to say, you know, the way this thing looks like it's really going to be kind of cumbersome. Whereas if it's a perfect model, you're going to go, it just is a human nature. You go, it's too perfect. I can't change that. So I think when you look at complexity, we also have to think about how do we use ambiguity to represent things appropriately.
There's so many questions one could ask. I mean, you think about Lewis and Clark, and they did all their own drawings of their trip.
Yeah.
You know, at that point in the world, people were trained to do that because
Yeah.
that was there weren't cameras.
Yeah.
And
They
we
couldn't
kind
use
of,
their iPhone to find out where they were.
yeah, and so we've gone from a stage where, you know, people did know some of that, and then we've gone to a time where basically speaking and writing and reading
Yeah.
are about all the same speed. And drawing is like impossible.
Yeah.
Right? Are we ever going to be at a place where people can communicate visually as fast as they can take it in? Who will be able to do that? How is that going to be, you know, what is the hierarchy? And then in terms of this whole ambiguity question, you know, how do we let people or train people to slide between, you know, reality and ambiguity in a visual form?
Yeah. I think that the fascinating thing when I showed you the thing about Sketchbook Mobile, fascinating thing that we saw is we always thought people wanted to draw things very precisely and you need a high level of skill to draw, which you do, you know, to do technical drawing. In fact, seeing the number of people who just want to use their finger and doodle and the stuff that they draw with that application, we got a whole picture gallery, you know, the kind of stuff they draw. So I think part of it is unleashing creativity in people to be able to know that it's okay to draw, to create ambiguity. I think it's sort of a refactoring. In some ways, we think of representation. We need to think about a refactoring of the tools. So if you think about education now, you know, when I was in school, when you went to class, you learned about, you know, how do you do research, right? You learned about using the library and the card catalog and all that stuff. Well, students today just Google it. And in fact, we don't need to remember facts as much because the facts are available to us instantaneously. In fact, we have a richer fact base we can get to than through the traditional methods. So just like we're kind of refactoring education to think more about thinking skills, less about memorizing a bunch of facts, I think representation we need to refactor in some way too, but I'm not quite sure what that is yet.
And also, again, it goes beyond visualization. I mean,
Yeah.
three-body diagram. You know, there's an iPad app right now I love it whenever I get surprised, because it's like when we get surprised, it's something really cool has come out of the lab. Touch screen, you're touching it, and you're changing the basic engineering. You're changing not just how it looks, I guess you would say, but how it works. So I guess if you
How
think
it performs.
how it performs, yeah. So I think when you look ahead, your question is, well, how would people work together? We're talking right now, so I think your point is visual communication. I think it becomes easier not just to create a visual representation, but also to morph it in real time. Again, the sketchbook stuff is wild, but this stuff is even wilder in a way. I think as it becomes easier, and touchscreen might be the way to go. The touchscreen is going to open up the actual doing the design of how it works to a whole new level of people. So it's
We're gonna move beyond touchscreens.
yeah,
You go 3D.
It'll be an intermediate phase, just like these guys are.
yeah. It's going to be the real.
Another question?
Sure.
Oh,
You're,
go ahead.
you're the one with the clock, so I'm.
So I have a question here.
Yeah.
I mean, you talked about the 3 C's.
Yeah.
Cognition, collaboration, communication.
Yeah.
I mean, I think all designers are dealing with this stuff,
Yes.
right? All these things.
Yeah.
And personally, I find, sort of like, there's no like single tool
Yeah.
that works for us, or even in any given part of the problem.
Yeah.
I'm moving between 3 or 4, doing the design thing. So I guess my question is for you guys is, well, assuming you have high-end tools that can do all this stuff and are highly integrated, what's down at the low end where there are only 3 or 4 people, we're not going to spend $100,000 or even $10,000 on a system.
Yeah.
And something beyond sketchbook. So an example is thinking about, you talk about, moving to sketching versus, tight drawing. I'm thinking about, well, I'm working on a problem which has to do with like traffic flowing through a system. Well, I'd like to just be able to like move little logo blocks or, start with that, and then can turn into a drawing.
So there's tangible issue.
Because even to be able to draw like this, well, there's a big level of skill.
Yeah.
And there's a lot of stuff you do that's like completely
Yeah.
unintelligible to somebody else. It's, beyond ambiguity. It's like
So,
incomprehensible.
so we think the app phenomenon on these kind of devices has been pretty interesting. It's the idea of doing something small and focused, but then being able to do more. We did an ethnographic study of our users, and our picture of people who use our software is they're people who sit there 8 hours a day in front of our application doing things. The older engineers do that. We actually did something I think she's about 22 years old. So we did a video of her, and it was much more of a mashup of tools. I mean, she was doing this, getting this from over here, and she used 12 different pieces of software in the period of like 10 minutes. And so I think that we get this interesting style question of, and then you get to the interoperability question of, so what information is really transferred, because the applications have a lot of knowledge embedded in them, and each one speaking a slightly different language. But we think that may be more the way people work. And we're really kind of grappling with that now.
I mean, I'm thinking that that's kind of like the goal. There's sort of like a sweet spot there.
Yeah.
It's not making this one really good and making this one really good. I mean, there's some like little mystery to be solved about how do you make it easy to quickly move while holding, carrying the spirit of the idea that you couldn't quite get here, carry it over here and make it easier.
And there's an interesting organizational challenge too, as you think about this inside a software company, because people view their goal as, I'm working on this thing, and it's to optimize this thing, getting them to say, no, we're working on this thing, this collection of things. It's a big culture shift that we're in the middle of.
So here you guys have, people that are running Autodesk here. I'm dreaming that a couple of the students, or one student, I guess we're out of time, one student would ask a question. Because, it's at university, everything, it's really good for you guys to ask questions. And if you guys can think of something about design you want to put forward or integrate.
How do you marry practical design and aesthetic design? Like looking at the auto example here, it's aesthetically pleasing, but if you can't fit all the electronics in that they want or all the features in that they want, how do you marry that?
Well, that's a very interesting question. Frank Lloyd Wright, there's a big debate in architecture. Does form follow function? Does function follow form? So the international style architects said form follows function. We design very functional things for the machine age. And Wright said, no, form and function are one. I think good designers see that in fact, good design really is a balance of form, function, and performance. And one of the challenges, though, is this kind of fragmentation of the process. So when you talk to industrial designers who do something like this, they're designing a shape of a car. And what they're really trying to do is create a particular feel. It's an emotion. And And to them, that's kind of paramount. That's what they're really trying to do. And one of the problems in a design process is that the tools to use to create the structural forms behind the shape were disconnected. So they would modify the shape, and the engineer would go, you're just changing it by like a couple millimeters, and the curvature is just changing a little bit. How could that affect it? But to the designer, that's a huge deal. So part of the issue is getting tools that actually are interconnected so they can have a dialogue rather than two monologues. And also there's also the human problem of saying, hey, look, I mean, if you talk to a hardcore structural engineer, they say, the designers, the cap with the ponytail, they'll kind of have that stereotype. They don't actually recognize that the designer actually has as legitimate a concern, but it's in a different realm, because they're actually trying to create a feel that, in fact, they probably got from their marketing folks saying, we want this car to appeal to this particular demographic and have this kind of feel, whereas the structural engineer has a different set of concerns. So I think part of it is tools, part of it's education, helping people appreciate a more balanced view of what they're doing, or a more integrated view of what they're doing.
So
Another layer to that, I think also when you look at technology and design, technology is the first thing to get commoditized, right, from the bottom up. So we talk about this all the time. It's an interesting place to be in. Design, and that's also commensurate with the experience, is sort of up here. It's sort of competitive. They will come from the bottom and commoditize the technology, so we have to make it better. But it's harder to come from the bottom or the side and commoditize the design. And I think in terms of what the customer values, as Steve Jobs' passing has made us even realize even more, the customer experience is largely the design. They appreciate the technology when it's hidden from them. For customers, the technology is a means, right? The experience and design is the end. Jobs understood that, as he famously said, Gates not necessarily. So I think this is a constant arms race between the two and between other companies. But we sort of look at design and innovation and the experience that whatever it is gives in the capital. Okay.
So just because we're out of time, I think we'll have to leave it at that. And I just want to make sure that our friends from Autodesk have some of our propaganda. There's a bag for you and a box. Thank you very much. Meet us outside for some cookies and insights.